Uncertainty in measurement. Exact numbers are numbers that are known with complete certainty. These include counting numbers, so if you count 3 apples, 3 would be considered an exact number. Defined values like 12 in a dozen, 1,000 grams in a kilogram, and 60 minutes in an hour are all examples of exact numbers as well. Inexact numbers are numbers that are measured. No matter what, measured quantities will have some level of uncertainty to them. This is because lab equipment is not perfect and has a limit of detection to what it can measure. We aim to measure quantities with both accuracy and precision. Accuracy is how closely measurements agree with the actual or true value. Say we know the weight of a block is 100 grams. If I measured the block to be 99.5 grams, that's pretty accurate because it's close to the true value of 100 grams. However, let's say I forgot to calibrate the scale and I measured the block to be 70 grams. This would not be accurate because it's not close to the true value of 100 grams. On the other hand, precision is a measure of how closely multiple measurements will agree with each other. A common metric for precision is standard deviation, which is how much data points differ or deviate from the mean. A lower standard deviation indicates a higher precision because the data points don't deviate from the mean very much, whereas a high standard deviation indicates the numbers are all over the place. You don't need to worry about calculating standard deviation, but you do need to be aware that it's commonly used to report the precision of an experiment. Numbers can also be written as the average plus or minus the standard deviation. So if we did 3 separate trials measuring the mass of the block to be close to 70 grams, then the measurements would be precise. The 3 measurements, while inaccurate because they're not close to the true value of 100 grams, would still be very precise because the standard deviation is very low. However, even if the average is close to the true value, the precision can still be low. Let's say the 3 measurements were all over the place, but the average comes out to be 100 grams. The accuracy of the mean would be high because the true value of the block is 100 grams. But the precision would be quite low because the standard deviation would be very high since the numbers are all over the place. Another important topic when discussing uncertainty is significant figures, or sig figs for short. Sig figs are the number of digits in a value or measurement necessary to decide the uncertainty of a measurement. Really, it answers the question, how many digits do I use in my final answer? Do I round to the nearest whole number, or do I write down all of the digits after the decimal place like my calculator reads? When in the lab and making scientific measurements, all digits are certain except for the last digit when reporting values. For example, measuring volume with a burette that marks every 0.1 milliliters would mean the scientist would then need to estimate to the next decimal point, like 1.42 milliliters. Another example would be measuring length with a meter stick that marks every 1 centimeter, means the scientist would then go to the next decimal place. So 52.3 centimeters in this case. There are 4 rules to determine what digits are significant in a number. First, all non-zero digits are significant. So if it's a number between 1 and 9, then it's significant. Second, zeros in between non-zero digits are always significant. So in these numbers, the highlighted zeros are in between non-zero digits and therefore are significant. Third, zeros at the beginning of a number are never significant. So in these examples, the first zeros would be considered placeholder zeros and are not significant. Fourth, zeros at the end of a number are significant if the number contains a decimal point. For example, in these numbers, there is a decimal point and therefore these zeros at the end are significant. You may also see numbers like this as well, and technically these zeros are significant, but you should always report your numbers in scientific notation rather than reporting it like this. Likewise, zeros at the end of a number without a decimal are not significant. So 217,000 would not have any significant zeros. 200 would only have 1 sig fig, and 17,000 would only have 2 sig figs. In addition, exact numbers like unit conversions have an infinite number of significant figures. We know with absolute certainty that 1,000 grams equals 1 kilogram, for example. Next, let's go over how to track significant figures in calculations. When we mathematically manipulate measured quantities, we don't want to lose or gain any certainty in our measurement. One important note is to only round the final answer to the correct number of significant figures. Do not round the intermediate steps, though you should keep track of all significant digits within the calculated quantities. There are 2 rules to follow when manipulating values. First, in multiplication and division, the result has the same number of significant figures as the quantity with the least amount of significant figures. Let's solve these equations and determine the amount of significant figures in each of them. First equation with multiplication. Okay, the first quantity, 2.73, has 3 non-zero digits, therefore has 3 significant figures. The second quantity, 12.001, has 5 significant figures because it has 3 non-zero digits and it has 2 zeros that are in between non-zero digits. And the last quantity, 1.810, has 3 non-zero digits and has 1 zero at the end with a decimal place. Therefore, there are 4 significant figures. The final answer, 59.3, should have 3 sig figs because the quantity with the least number of significant figures in our equation had 3 sig figs. Another equation, this time with division. Okay, the value on top has 4 non-zero digits and therefore has 4 significant figures. The value on the bottom has 3 non-significant placeholder zeros, but then has 2 non-zero digits and then 1 zero in between non-zero digits, therefore has 3 significant figures. The final answer will get you something like this, but because the number with the least number of sig figs was 3, we have to report our answer like this in scientific notation. Alright, on to the second rule when mathematically manipulating quantities. In addition and subtraction, the result has the same number of decimal places as the value with the least number of decimal places. Let's solve a couple of equations to demonstrate this. Here's the first equation. 2.816 has 3 decimal places. 1.7 has 1 decimal place, and 5.1647 has 4 decimal places. Therefore, when adding these together, the final answer should have 1 decimal place, and so the final answer is 9.7. On to the next example. 15.68 has 2 decimal places. 32.128 has 3 decimal places, and 24.28 has 2 decimal places. Therefore, the final answer is 23.53. So remember, multiplication and division depend on the number of significant figures, whereas addition and subtraction depend on the number of decimal places. Let's do a couple of examples merging the 2 rules together. Let's solve what's in the parentheses first. 8.72 minus 6.1711, we get 2.5489, and we'll use this for the rest of the calculation and don't round until the end. But we need to remember that the least significant digit is in the second decimal place and that there are 3 sig figs in this value. Multiply this out and we get something like this for our answer, but because we need to truncate to 3 sig figs, our final answer is 174. Alright, next example. Let's add the numbers on the top and subtract the numbers on the bottom. Now we have to do multiplication and division, and the number with the least number of sig figs is on the bottom, which has 2 significant figures. After calculating the result, you'll get something like this, but because we need to cut to 2 sig figs, the final answer is 91. Please hit that subscribe button if you haven't already. Thank you for watching, and I hope you learned a thing or two about science.